Pluto, once considered the ninth planet of our solar system, has long been a subject of fascination and intrigue. Its status, characteristics, and discovery have all played a pivotal role in shaping our understanding of not just this distant celestial body, but the broader solar system as a whole. Though demoted from planetary status in 2006, Pluto remains a critical part of discussions about space, planetary science, and the ever-evolving ways we classify celestial objects. To appreciate Pluto fully, it's important to dive deep into its history, the characteristics that distinguish it, its role within the Kuiper Belt, and what its journey tells us about the future of space exploration. Before we continue the video, subscribe to the channel so you don't miss out on any of these videos. Pluto was discovered in 1930 by Clyde Tombaugh, an American astronomer who was diligently searching for a theoretical ninth planet. This mysterious planet had been predicted based on irregularities in the orbits of Uranus and Neptune. Initially termed Planet X, Pluto was the answer to a long-running quest to understand the outer solar system, and it became a symbol of humanity's desire to explore the unknown. For more than 7 decades, Pluto was celebrated as the smallest, most distant planet, orbiting the Sun in a wide elliptical path that took it far beyond Neptune and into the icy outer reaches of the solar system. However, the discovery of Pluto opened new questions. Even in 1930, astronomers noticed that Pluto was different from the other planets. For one thing, it was extremely small, smaller than Earth's moon, with a diameter of just 2,376 kilometers. It also had a highly eccentric orbit, inclined at a steep angle compared to the more regular orbits of the other planets. Pluto also crossed Neptune's orbit, meaning that, for a period during its long 248-year journey around the Sun, it came closer to the Sun than Neptune. Yet for all its oddities, Pluto was embraced as a planet until advancements in astronomical technology and deeper studies of the outer solar system began to suggest it was not alone. In the 1990s, astronomers began discovering other objects in the region of space where Pluto resided. These objects, known as trans-Neptunian objects, TNOs, varied in size, shape, and composition, but some of them were strikingly similar to Pluto. One such object, discovered in 2005, was Eris. Eris is about the same size as Pluto and has a similar elliptical orbit. The discovery of Eris raised important questions. If Pluto was a planet, then why not Eris? If Pluto was not a planet, then what was it? This led to one of the most famous debates in modern astronomy. What exactly is a planet? In 2006, the International Astronomical Union, IU, met to redefine the term. According to the new definition, a planet must meet 3 criteria. It must orbit the Sun, it must be spherical in shape due to its own gravity, and it must have cleared its orbit, meaning it must be gravitationally dominant enough to have removed other debris from its orbital path. While Pluto meets the first 2 criteria, it does not meet the third, as it shares its orbit with other objects in the Kuiper Belt. As a result, Pluto was reclassified as a dwarf planet, a term that, while still recognizing its planetary characteristics, set it apart from the 8 main planets. The reclassification of Pluto ignited a firestorm of controversy, with many people feeling an emotional attachment to Pluto as the 9th planet. For astronomers, however, the debate was less about sentimentality and more about precision. The new definition of a planet was designed to accommodate the growing knowledge of the solar system. It reflected the discoveries of objects similar to Pluto in the Kuiper Belt and was meant to offer clarity in distinguishing between the classical planets and these smaller, icy worlds. The Kuiper Belt itself is one of the most fascinating regions of the solar system. It is a vast, donut-shaped zone of icy bodies that extends beyond Neptune. Pluto is one of the largest objects in this region, but it is far from the only one. Thousands of Kuiper Belt objects, KBOs, have been discovered since the 1990s, and many of them resemble Pluto in size and composition. These objects are remnants from the early solar system, a time when the Sun and planets were still forming. The Kuiper Belt, therefore, offers a window into the solar system's distant past, preserving material that has changed very little since the solar system's formation. In this sense, Pluto and its Kuiper Belt companions represent a kind of fossil record of the early solar system. The study of these objects can help scientists understand how planets form and evolve. Moreover, by comparing Pluto to other KBOs, astronomers can gain insight into the diversity of planetary bodies that exist in our solar system and beyond. One of the most exciting developments in Pluto research came in 2015, when NASA's New Horizons spacecraft made its historic flyby of Pluto. This mission, launched in 2006, had the ambitious goal of providing the first close-up images and data of this distant world. After traveling for nearly a decade and covering more than 3 billion miles, New Horizons finally reached Pluto, revealing it in unprecedented detail. The images sent back by New Horizons transformed our understanding of Pluto. Instead of a cold, dead world, Pluto was revealed to be a geologically active body with a complex surface. One of the most surprising discoveries was the presence of vast plains of nitrogen ice, some of which appeared to be relatively young, suggesting ongoing geological processes. Pluto's surface also featured towering mountains made of water ice, as well as strange, flowing glaciers composed of nitrogen and methane. Perhaps the most iconic feature of Pluto is its heart, a large, bright region on its surface known as Sputnik Planitia. This heart-shaped plain is made of nitrogen ice and is thought to be a site of convection, where heat from the interior causes the ice to rise and sink in a slow, churning process. This discovery was a major surprise, as scientists had not expected such activity on a small, distant world like Pluto. Another fascinating aspect of Pluto is its atmosphere, which is composed mainly of nitrogen, with traces of methane and carbon monoxide. Pluto's atmosphere is extremely thin, but it extends far into space, forming a halo of gas around the planet. During its flyby, New Horizons was able to measure the composition and structure of Pluto's atmosphere, providing valuable data on how it interacts with the solar wind and the surrounding environment. One of the more surprising findings was the discovery of haze layers in Pluto's atmosphere, which form as sunlight breaks down methane and other gases, creating complex hydrocarbons that settle to the surface. Pluto's atmosphere is also highly dynamic. Because of its eccentric orbit, Pluto moves closer to and farther from the Sun during its 248-year journey. When Pluto is closer to the Sun, its surface warms slightly, causing frozen nitrogen to sublimate into gas and creating a temporary atmosphere. As Pluto moves farther from the Sun, the atmosphere can freeze and fall back to the surface as snow or frost. Pluto's 5 moons also add to its intrigue. The largest, Charon, is almost half the size of Pluto itself, making it the largest moon relative to its parent body in the solar system. Charon and Pluto are tidally locked, meaning they always show the same face to each other. This has led some astronomers to consider Pluto and Charon a binary system, as they orbit a point in space between them, rather than one body orbiting the other. Charon is also geologically interesting, with a surface marked by canyons, ridges, and plains. Like Pluto, Charon shows signs of past geological activity, including what appears to be a vast, frozen ocean of water ice. The relationship between Pluto and Charon is a subject of ongoing study, as scientists try to understand how this binary system formed and evolved over time. In addition to Charon, Pluto has 4 smaller moons: Nix, Hydra, Kerberos, and Styx. These moons are much smaller and less studied than Charon, but their discovery has added complexity to the Pluto system. Nix and Hydra were discovered in 2005, followed by Kerberos in 2011 and Styx in 2012. The presence of these moons suggests that Pluto experienced a violent past, possibly involving a collision that created this family of satellites. The moons have irregular shapes, and their orbits are somewhat chaotic, likely due to the gravitational influence of Pluto and Charon. The discovery of Pluto's moons and the details of their orbits raise fascinating questions about how small celestial bodies in the outer solar system form and evolve. Studying these moons not only enhances our understanding of Pluto but also provides clues about the dynamics of other planetary systems, both in our solar system and beyond. In particular, Pluto's system gives us insight into the nature of binary and multi-body systems, which are more common than previously thought. Another significant topic when discussing Pluto is its role as the prototype for a whole new class of objects, the dwarf planets. When Pluto was demoted in 2006, it wasn't merely reclassified, it became the first example of a new category. Dwarf planets are objects that orbit the Sun and are large enough to be rounded by their own gravity but haven't cleared their orbital paths. This category includes Pluto, Eris, Haumea, Makemake, and Ceres, with the potential for more dwarf planets to be discovered in the future. The Kuiper Belt, where Pluto resides, is home to many other similar bodies, some of which may also qualify as dwarf planets. In fact, the discovery of Eris, which is similar in size to Pluto, was one of the primary drivers behind the need to reconsider what constitutes a planet. As more objects like Eris are discovered, the classification of these icy bodies becomes an ongoing debate in planetary science. Eris, for example, is slightly more massive than Pluto but resides even farther from the Sun, adding to the complexity of understanding the outer reaches of our solar system. The classification of dwarf planets reflects a broader shift in how astronomers view the solar system. Rather than seeing it as a set of distinct planets orbiting in neat, predictable patterns, modern astronomy views the solar system as a much more dynamic, complex place. Objects like Pluto and Eris challenge the traditional view of what a planet is and push us to consider new frameworks for understanding the multitude of objects that populate the solar system. As we explore Pluto and its surrounding environment, we also gain insight into the nature of planetary formation. Pluto and other Kuiper Belt objects are thought to be remnants from the early solar system, frozen in time since the planets first formed. These bodies are made of ice, rock, and organic compounds, offering clues about the conditions that existed in the outer solar system billions of years ago. By studying them, scientists can learn more about how planets like Earth formed and how the solar system evolved into the structure we see today. One of the most exciting aspects of studying Pluto is the possibility that it could harbor organic molecules or even conditions conducive to life. While Pluto is far too cold to support life as we know it, the presence of organic compounds on its surface, detected by New Horizons, raises intriguing possibilities. Organic molecules are the building blocks of life, and their presence on Pluto suggests that the raw materials for life may be more common in the solar system than previously thought. Furthermore, the discovery of a subsurface ocean on Pluto, which may still contain liquid water, opens the door to the possibility of life existing in some form, even in this distant, frozen world. The idea of a subsurface ocean on Pluto has become one of the most intriguing discoveries from the New Horizons mission. Based on the data collected, scientists believe that there may be a layer of liquid water beneath Pluto's icy crust, kept warm by heat from radioactive decay in the planet's core. This potential ocean could be similar to those believed to exist on moons like Europa and Enceladus, where the combination of water, heat, and organic molecules could create environments where life might thrive. While the existence of life on Pluto remains purely speculative, the possibility that such environments exist beyond Earth continues to fuel our curiosity and drive future exploration. The discovery of Pluto's potential ocean also raises broader questions about where we might find habitable environments in the solar system. Traditionally, planets in the habitable zone, the region around a star where conditions are just right for liquid water, were considered the most likely places to find life. However, discoveries like those on Pluto, Europa, and Enceladus suggest that life could exist in far more extreme environments than previously thought. The search for life has expanded beyond the traditional planets to include icy moons, dwarf planets, and even comets, where water and organic molecules are present. Exploring Pluto also provides a unique opportunity to study the effects of extreme distance from the Sun. Pluto receives only a tiny fraction of the sunlight that reaches Earth, and its surface temperatures can plunge to nearly -400 degrees Fahrenheit. Despite these frigid conditions, Pluto's surface shows signs of change and activity. The existence of flowing ice, geological formations, and atmospheric processes demonstrates that even in the coldest, most distant reaches of the solar system, planetary bodies can be dynamic and evolving. The demotion of Pluto sparked not just scientific debate but also emotional reactions from people who had grown up thinking of Pluto as the ninth planet. Petitions, campaigns, and even children's books were written in defense of Pluto's planetary status, showing how deeply ingrained it had become in popular culture. The controversy surrounding Pluto's reclassification also speaks to the broader human desire for clear, simple definitions in a universe that is anything but simple. As our understanding of the cosmos expands, Pluto reminds us that the boundaries of knowledge are always shifting, and that scientific classification is a tool that must evolve with new discoveries. Pluto's cultural impact extends beyond the realm of planetary science. Its unique characteristics and mysterious nature have inspired countless works of fiction, art, and music. From its early discovery to its reclassification as a dwarf planet, Pluto has been a subject of fascination in science fiction, where it is often depicted as a remote, cold world on the fringes of the solar system. This image of Pluto as an outlier, both scientifically and culturally, continues to captivate the imagination of people around the world. In many ways, the exploration of Pluto is a microcosm of the broader human quest to explore the unknown. The New Horizons mission was a bold endeavor, sending a spacecraft billions of miles to a world we had never seen up close. The success of this mission demonstrated the power of human ingenuity and the potential of space exploration. It also highlighted the importance of persistence and patience. The journey to Pluto took nearly a decade, but the data and images it provided have fundamentally changed our understanding of the outer solar system. Pluto also serves as a reminder of how much we still have to learn about our own cosmic neighborhood. The solar system is vast and filled with countless objects that we have only begun to explore. As technology improves and new missions are launched, our understanding of Pluto and other distant worlds will continue to evolve. Future missions to the Kuiper Belt, for example, could provide more detailed information about Pluto's composition, its moons, and its place in the broader context of the solar system. The study of Pluto and the Kuiper Belt is not just about understanding our solar system. It also has implications for the study of planetary systems around other stars. The discovery of exoplanets, planets orbiting other stars, has opened a new frontier in astronomy. Many of these distant worlds share similarities with Pluto and other Kuiper Belt objects, and studying our own solar system can provide valuable insights into how these distant planetary systems form and evolve. The study of Pluto and its environment also touches on some of the biggest questions in science. How do planets form? What conditions are necessary for life? What is the fate of planetary systems over time? Pluto, despite its small size and distance, plays a crucial role in helping us answer these questions. Its unique characteristics, from its atmosphere to its potential subsurface ocean, challenge our assumptions and push the boundaries of what we thought was possible. As we continue to study Pluto, it becomes clear that this small, distant world offers a window into the history of the solar system. Pluto and its neighbors in the Kuiper Belt are thought to be some of the most ancient objects in the solar system, largely unchanged since they formed billions of years ago. By studying these objects, scientists can learn more about the conditions that existed in the early solar system and the processes that led to the formation of planets. The Kuiper Belt itself is a region rich with icy bodies and dwarf planets, which are remnants of the protoplanetary disk that surrounded the young Sun. These bodies contain clues about the building blocks of planets and the events that shaped the solar system's evolution. One of the most fascinating aspects of studying Pluto is the opportunity to compare it with other dwarf planets and Kuiper Belt objects. Each of these objects has its own unique characteristics, yet they also share similarities that provide insight into the broader processes at work in the outer solar system. For example, Eris, Haumea, and Makemake, three of the largest known dwarf planets, each have distinct features, such as different shapes, surface compositions, and orbital properties. By comparing these objects, scientists can begin to piece together a more complete picture of the Kuiper Belt and the diversity of objects it contains. Eris, in particular, has drawn significant attention due to its size and distance from the Sun. Discovered in 2005, Eris is slightly smaller in diameter than Pluto but more massive. Its discovery was a key factor in the reclassification of Pluto, as it challenged the notion of what constitutes a planet. Eris's surface is extremely reflective, likely due to a layer of frozen methane, and it orbits the Sun at a much greater distance than Pluto, making it one of the most distant known objects in the solar system. Eris's orbit is highly eccentric, meaning that it moves closer to and farther from the Sun over the course of its orbit, which takes 558 Earth years to complete. Haumea, another intriguing dwarf planet, is notable for its elongated shape, which is believed to be the result of its rapid rotation. Haumea rotates once every 4 hours, making it one of the fastest spinning large objects in the solar system. This rapid rotation causes Haumea to take on a stretched, ellipsoidal shape rather than the more typical spherical shape of other dwarf planets. Haumea also has 2 known moons, Hyaka and Amaka, and is surrounded by a ring of icy debris, making it a particularly complex and fascinating object for study. Makemake, the third of the large known dwarf planets in the Kuiper Belt, has a much more reflective surface than Pluto or Eris, suggesting that it is covered in methane ice. Discovered shortly after Eris, Makemake was one of the objects that led to the redefinition of the term planet by the International Astronomical Union, IAU. Makemake's lack of a known atmosphere and its distance from the Sun make it a particularly cold and inhospitable world, but like Pluto, it offers valuable insight into the diversity of the outer solar system. The exploration of Pluto and these other distant objects is helping scientists refine their understanding of planetary formation. One of the key questions that arises from studying dwarf planets is how such small, icy bodies manage to form so far from the Sun. The leading theory is that these objects are remnants from the early solar system, left over from the process that formed the larger planets. However, the details of how these objects came to be, and why they did not grow larger to become full-fledged planets, remain areas of active research. Another important question concerns the composition of Pluto and other dwarf planets. These objects are composed primarily of ice and rock, but they also contain a variety of other materials, including organic compounds. The presence of these compounds on Pluto, Eris, and other dwarf planets is particularly intriguing because it suggests that the building blocks of life may be widespread throughout the solar system. Organic molecules are essential for the development of life, and their presence on Pluto raises the possibility that similar compounds could be found elsewhere in the Kuiper Belt, or even beyond. In addition to studying the surface composition of these objects, scientists are also interested in their internal structures. The discovery of a subsurface ocean on Pluto, for example, raises the possibility that other dwarf planets could also have hidden reservoirs of liquid water beneath their icy crusts. If this is the case, it would have significant implications for the search for life in the outer solar system. The presence of liquid water is considered one of the key ingredients for life, and the discovery of subsurface oceans on multiple objects in the Kuiper Belt would greatly expand the number of potentially habitable environments in the solar system. The idea that life could exist on Pluto, or on other icy bodies in the outer solar system, remains speculative, but it is a topic of great interest to astrobiologists. The discovery of extremophiles, organisms that thrive in extreme environments on Earth, has expanded the range of environments in which life might be able to survive. On Earth, extremophiles can be found in environments as diverse as deep-sea hydrothermal vents, acidic hot springs, and frozen glaciers. These organisms have adapted to survive in conditions that were once thought to be too harsh for life, suggesting that life could potentially exist in similarly extreme environments elsewhere in the solar system. If life were to exist on Pluto, it would likely be in the form of microbes living in the subsurface ocean. Such life would have to be able to survive in complete darkness, under high pressure, and at extremely low temperatures. While this might seem unlikely, it is worth noting that similar conditions exist in some of Earth's most extreme environments, such as the deep oceans and the polar ice caps. The discovery of life in these environments has led scientists to consider the possibility that life could exist in even more extreme conditions, such as those found on Pluto. The potential for life on Pluto, and on other icy worlds like Europa and Enceladus, has spurred interest in future missions to explore these distant bodies. While the New Horizons mission provided a wealth of information about Pluto, it was only a flyby mission, meaning that it did not land on the surface or stay in orbit for an extended period. Future missions could involve orbiters, landers, or even submarines designed to explore the subsurface oceans of these worlds. Such missions would provide more detailed information about the composition of these bodies, their geological activity, and the potential for life. As our understanding of Pluto and the Kuiper Belt continues to grow, it also raises important questions about the broader context of the solar system. For example, how does the Kuiper Belt fit into the overall structure of the solar system? Is it a remnant of the early solar system, or could it be part of a much larger structure that extends far beyond Pluto's orbit? Some scientists believe that the Kuiper Belt is just the inner edge of a much larger region known as the Oort cloud, which is thought to contain trillions of icy bodies that stretch halfway to the nearest stars. While the existence of the Oort cloud has not been directly confirmed, it is considered the likely source of long-period comets that occasionally enter the inner solar system. The exploration of Pluto and the Kuiper Belt also has implications for the study of exoplanets, planets that orbit stars other than the Sun. Many of the exoplanets discovered to date are icy bodies located far from their parent stars, similar to Pluto and other Kuiper Belt objects. By studying Pluto and its neighbors, scientists can gain a better understanding of how these distant exoplanets form and evolve. In particular, the discovery of complex atmospheric and geological processes on Pluto suggests that similar processes could be at work on icy exoplanets, even in the extreme conditions of the outer regions of planetary systems. Pluto is far more than just a distant, icy dwarf planet. Its exploration has transformed our understanding of the solar system, challenging old ideas and opening up new avenues of research. From its dynamic surface to its potential subsurface ocean, Pluto continues to surprise and intrigue scientists, offering valuable insights into the history and evolution of the solar system. As we continue to study Pluto and its fellow dwarf planets, we are not only learning more about these distant worlds, but also gaining a deeper understanding of our place in the cosmos. The story of Pluto is far from over, and future missions and discoveries will undoubtedly continue to reshape our understanding of this enigmatic world. The ongoing exploration of Pluto is part of a broader effort to understand the outer reaches of the solar system, a region that remains largely mysterious. As we look farther into space, it's becoming increasingly clear that our solar system is more diverse and complex than we ever imagined. Pluto, once dismissed as little more than a distant, icy speck, has proven to be a dynamic and geologically active world with many secrets left to uncover. What we have learned about Pluto so far is only the beginning. One of the most significant revelations from the New Horizons mission was the discovery of Pluto's surprisingly complex atmosphere. Despite its small size and great distance from the Sun, Pluto has an atmosphere composed primarily of nitrogen, with traces of methane and carbon monoxide. This atmosphere is thin and tenuous, but it is highly dynamic, with seasonal variations and the potential for localized weather patterns. The presence of an atmosphere on such a small, distant world was unexpected and has led to a reevaluation of what we thought we knew about the conditions necessary for atmospheres to form and persist. Pluto's atmosphere also offers a unique opportunity to study atmospheric escape, the process by which gases escape from a planet's atmosphere into space. This process occurs on all planets with atmospheres, but it is particularly pronounced on small, low-gravity bodies like Pluto. On Pluto, the thin atmosphere is constantly leaking into space as particles are swept away by the solar wind, a stream of charged particles emitted by the Sun. This process is thought to be responsible for the gradual loss of Pluto's atmosphere over time, but the details of how atmospheric escape works on Pluto, and how long its atmosphere might last, are still being studied. One of the key questions that scientists are trying to answer is how Pluto's atmosphere interacts with its surface. The nitrogen, methane, and other gases in Pluto's atmosphere are thought to originate from surface ices that sublimate, or turn directly from solid to gas, as Pluto's surface heats up during its orbit around the Sun. This process is similar to what happens on comets when they approach the Sun, and it suggests that Pluto's surface and atmosphere are closely linked. As Pluto moves farther from the Sun, its atmosphere may freeze out, condensing back onto the surface as frost. This seasonal cycle of sublimation and condensation is a key area of study for planetary scientists, as it may provide clues about similar processes on other icy bodies in the solar system. Another intriguing aspect of Pluto's atmosphere is the presence of haze layers that extend high above the surface. These haze layers are composed of tiny particles that form when sunlight interacts with methane and other gases in the atmosphere, creating complex organic molecules called tholins. Tholins are responsible for the reddish coloration seen on many icy bodies in the outer solar system, including Pluto's surface. The discovery of these haze layers on Pluto was unexpected and has led to new questions about the processes that drive atmospheric chemistry on distant worlds. In addition to its atmosphere, Pluto's surface is a rich and varied landscape, featuring a wide range of geological features. One of the most striking of these is Sputnik Planitia, a vast, heart-shaped plain of nitrogen ice that dominates Pluto's surface. Sputnik Planitia is thought to be a relatively young feature, as it shows few impact craters, suggesting that it has been resurfaced by geological processes within the last few million years. This resurfacing may be driven by convection within the nitrogen ice, as warmer material rises and cooler material sinks, creating a constantly shifting surface. Sputnik Planitia also appears to be a gravitational anomaly, as it is located directly opposite Charon, Pluto's largest moon. This suggests that the formation of Sputnik Planitia may have been influenced by Pluto's interaction with Charon, possibly as a result of a giant impact that created the moon. The relationship between Pluto and Charon is unique in the solar system, as the two bodies are tidally locked, meaning that they always show the same face to each other, as they orbit a common center of mass. This close relationship has likely played a significant role in shaping both Pluto's and Charon's evolution over time. Charon itself is a fascinating world, with a surface that is distinctly different from Pluto's. While Pluto's surface is dominated by nitrogen and methane ices, Charon's surface is primarily composed of water ice. Charon also features a large canyon system, which stretches for more than 1,000 kilometers across its surface. This canyon system is thought to be the result of tectonic activity, as Charon's interior cooled and contracted, causing the surface to crack and form deep chasms. In addition to its geological features, Charon also shows evidence of cryovolcanism, or ice volcanism, in which volatile materials like water, ammonia, and methane are ejected from the interior to the surface. The relationship between Pluto and Charon extends beyond their physical interaction. The two bodies are also linked by their shared history, as both are thought to have formed from a giant impact early in the solar system's history. This impact would have created a debris disk around Pluto, from which Charon and possibly some of Pluto's smaller moons coalesced. This giant impact hypothesis is similar to the leading theory for the formation of Earth's moon, and it suggests that giant impacts may play a significant role in shaping the moons of planets and dwarf planets throughout the solar system. In addition to Charon, Pluto has 4 smaller moons: Styx, Nix, Kerberos, and Hydra. These moons are much smaller than Charon and have irregular shapes, suggesting that they may be captured objects from the Kuiper belt rather than remnants of the giant impact that formed Charon. The orbits of these moons are also highly chaotic, as they are influenced by the gravitational interactions between Pluto and Charon. This chaotic motion makes predicting the long-term behavior of these moons difficult, but it provides a unique opportunity to study the dynamics of multi-body systems in the outer solar system. The discovery of Pluto's moons has also raised questions about the potential for additional, undiscovered moons or even rings around Pluto. While no rings have been detected so far, the possibility remains that small, faint rings could exist, formed by debris from impacts on Pluto's moons. The presence of rings around distant icy bodies is not unheard of, as similar ring systems have been discovered around other small objects in the outer solar system, such as the dwarf planet Haumea. Future missions to Pluto could help to answer these questions by providing more detailed observations of its moons and any potential rings. As we look to the future, the exploration of Pluto and the Kuiper belt is likely to continue to be a major focus for planetary scientists. The New Horizons mission was just the first step in what will likely be a long and fruitful exploration of this distant region. Future missions could include orbiters that study Pluto and its moons in greater detail, landers that explore the surface and search for signs of a subsurface ocean, or even spacecraft that venture farther into the Kuiper Belt to study other dwarf planets and icy bodies. The next logical step in Pluto exploration could be a return mission with more advanced technology, allowing for a more comprehensive study of its surface, atmosphere, and moons. Such a mission could also include instruments designed to search for signs of life, such as organic molecules or microbial activity. While the prospect of life on Pluto remains speculative, the discovery of a subsurface ocean and the presence of complex organic molecules make it an intriguing possibility that warrants further investigation. The study of Pluto is also part of a broader effort to explore the outer solar system and understand its role in the formation and evolution of the planets. The outer solar system is a region that remains largely unexplored, but it is home to some of the most intriguing and potentially habitable worlds in the solar system, including the icy moons of Jupiter and Saturn, as well as the distant dwarf planets of the Kuiper Belt. By studying these objects, scientists can gain valuable insights into the processes that shaped the early solar system and the conditions that might support life on other worlds. In conclusion, Pluto's exploration has transformed our understanding of the outer solar system and raised new questions about the formation and evolution of planetary bodies. From its complex atmosphere to its dynamic surface and potential subsurface ocean, Pluto has proven to be a far more interesting and diverse world than we ever imagined. As we continue to study Pluto and its fellow dwarf planets, we are gaining valuable insights into the history of the solar system and the potential for life in the most unexpected places. As we delve deeper into Pluto's mysteries, it becomes clear that its study is not only about understanding a distant, icy world but also about broadening our knowledge of planetary processes across the solar system and even beyond. Pluto's complex geology, dynamic atmosphere, and intriguing moons are examples of how diverse planetary bodies can be, even in regions where we once thought conditions were too extreme for active geological or atmospheric processes. Pluto's position in the Kuiper Belt places it in a particularly interesting context. The Kuiper Belt is a vast region beyond Neptune that contains a large number of small icy bodies, remnants from the early solar system. These Kuiper Belt objects, KBOs, vary widely in size, composition, and orbital characteristics, offering scientists a wealth of information about the processes that govern the formation of the solar system. Pluto, as one of the largest KBOs, serves as an important case study in understanding the Kuiper Belt as a whole. The Kuiper Belt itself is an area of intense study, as it contains clues to the early solar system's structure and dynamics. Unlike the inner planets, which have undergone significant evolution due to gravitational interactions, solar heating, and geological processes, many KBOs are thought to be relatively pristine, having remained largely unchanged since their formation. This makes them valuable time capsules, preserving the conditions and materials from the early solar system. Studying these bodies, including Pluto, helps scientists piece together the history of the solar system's formation and evolution. Pluto's discovery in 1930 by Clyde Tombaugh was a landmark event in astronomy, marking the first identification of a Kuiper Belt object. At the time, Pluto was thought to be the 9th planet in the solar system, but its small size and unusual orbit eventually led to questions about its classification. In 2006, the International Astronomical Union, IAU, reclassified Pluto as a dwarf planet, a decision that sparked significant debate within both the scientific community and the public. This reclassification was based on a new definition of what constitutes a planet, which required a body to have cleared its orbit of other debris. Pluto, residing in the Kuiper Belt, shares its orbit with other KBOs, which led to its demotion. Despite its reclassification, Pluto remains an object of great interest and fascination. Its complex features and unique position in the solar system challenge our understanding of planetary science and blur the lines between traditional categories of planets, moons, and smaller solar system bodies. The debate over Pluto's planetary status has led to a broader conversation about how we define planets and how we categorize the diverse range of objects in the solar system. Some astronomers argue that Pluto should still be considered a planet, pointing to its spherical shape, atmosphere, and geological activity as evidence that it meets many of the traditional criteria for a planet. Others contend that the new definition of a planet, which excludes bodies that share their orbits with other objects, is necessary to reflect our growing understanding of the solar system's complexity. Beyond its classification, Pluto has provided key insights into the processes that shape icy worlds in the outer solar system. One of the most significant discoveries made by the New Horizons mission was the presence of glaciers on Pluto's surface. These glaciers, composed primarily of nitrogen ice, are located in Sputnik Planitia, the heart-shaped basin that dominates Pluto's surface. The movement of these glaciers is driven by the sublimation of nitrogen ice, which occurs when sunlight warms the surface and causes the ice to turn directly into gas. This process creates pressure gradients that cause the nitrogen ice to flow across the surface, much like glaciers on Earth. The discovery of glaciers on Pluto was surprising, as it indicated that the dwarf planet's surface is geologically active, despite its small size and distance from the Sun. This geological activity is thought to be driven by heat from Pluto's interior, which may be the result of radioactive decay or tidal heating from its interaction with Charon. The presence of active glaciers also raises the possibility that other small, icy bodies in the outer solar system could be geologically active as well, challenging previous assumptions about the dynamics of these distant worlds. Another intriguing aspect of Pluto's surface is the presence of cryovolcanoes, or ice volcanoes. These features, which are found in the southwestern region of Pluto's surface, are thought to be the result of the eruption of volatile materials such as water, ammonia, or methane from the interior. Unlike traditional volcanoes, which erupt molten rock, cryovolcanoes eject icy slurries that can flow across the surface and reshape the landscape. The discovery of cryovolcanism on Pluto was unexpected, as it suggests that the dwarf planet's interior is warm enough to support the movement of liquid materials, despite its cold surface temperatures. Cryovolcanism is a process that has been observed on other icy bodies in the solar system, including Saturn's moon Enceladus and Jupiter's moon Europa. These moons, like Pluto, are thought to have subsurface oceans, and their geological activity is believed to be driven by tidal forces exerted by their parent planets. On Pluto, however, the source of heat driving cryovolcanism is less clear. Some scientists speculate that Pluto's interior could be heated by radioactive decay of elements like potassium and thorium, while others suggest that the gravitational interaction between Pluto and Charon may generate enough heat to maintain a subsurface ocean. The possibility of a subsurface ocean on Pluto is one of the most exciting discoveries made by the New Horizons mission. The presence of an ocean beneath Pluto's icy crust raises the possibility that this distant world could harbor the conditions necessary for life. While the surface of Pluto is far too cold to support life as we know it, a subsurface ocean, insulated by a thick layer of ice, could provide a stable environment where liquid water and organic molecules interact. These conditions are similar to those found on other icy moons in the outer solar system, such as Europa and Enceladus, which are considered prime candidates for the search for extraterrestrial life. The potential for life on Pluto remains speculative, but the discovery of a subsurface ocean has opened up new avenues of research into the habitability of icy worlds. Scientists are now studying the chemistry of Pluto's surface and atmosphere in greater detail, looking for signs of organic molecules that could serve as the building blocks of life. The presence of tholins on Pluto's surface, complex organic molecules formed by the interaction of sunlight with methane and other gases, suggests that the chemistry necessary for life could be present on this distant world. The study of Pluto is also shedding light on the processes that govern the formation and evolution of moons in the outer solar system. Charon, Pluto's largest moon, is thought to have formed from a giant impact early in the solar system's history, similar to the leading theory for the formation of Earth's moon. This giant impact would have created a debris disk around Pluto, from which Charon coalesced. The interaction between Pluto and Charon has likely played a significant role in shaping both bodies, as they are tidally locked, meaning they always show the same face to each other. The other moons of Pluto, Styx, Nix, Kerberos, and Hydra, are much smaller than Charon and have irregular shapes, suggesting that they may be captured objects from the Kuiper belt rather than remnants of the giant impact that formed Charon. These moons have highly chaotic orbits, influenced by the gravitational interactions between Pluto and Charon, making their long-term behavior difficult to predict. The discovery of these small moons has raised new questions about the formation and evolution of moons in the outer solar system, and future missions to Pluto could provide more detailed observations of their characteristics. Pluto's exploration has not only transformed our understanding of the dwarf planet itself but has also provided valuable insights into the broader processes that govern the solar system's formation and evolution. The New Horizons mission, which was the first to visit Pluto, has opened up new avenues of research into the Kuiper belt and the outer solar system. Future missions to Pluto and its fellow KBOs will likely continue to expand our knowledge of these distant worlds, providing new clues about the history and dynamics of the solar system. Pluto's exploration remains far from complete, with many questions still lingering about its geology, atmosphere, and potential for harboring life. As the furthest known world from the Sun in the solar system, excluding the occasional trans-Neptunian object that might travel further, Pluto represents an intriguing frontier for planetary science and astrobiology. Its distant position makes it one of the coldest objects in the solar system, with surface temperatures averaging around -375 degrees Fahrenheit -225 degrees Celsius, cold enough for volatile substances such as nitrogen, methane, and carbon monoxide to freeze into ice. Yet, beneath this frigid exterior, there may be warmth, geological activity, and even subsurface oceans. Pluto's atmosphere, while thin, plays a significant role in shaping the planet's surface. Composed primarily of nitrogen, with traces of methane and carbon monoxide, Pluto's atmosphere undergoes dramatic changes as it moves through its elliptical orbit around the Sun. When Pluto is closer to the Sun, during perihelion, its surface warms slightly, causing some of the nitrogen and methane ices to sublimate and form a thin atmosphere. As Pluto moves farther away from the Sun, during aphelion, the atmosphere freezes back onto the surface, forming frost. This seasonal variation has profound implications for the planet's weather patterns and surface conditions. One of the most fascinating aspects of Pluto's atmosphere is the presence of haze layers that extend up to 100 miles, 160 kilometers, above the surface. These haze layers are believed to form when sunlight interacts with methane in the atmosphere, triggering chemical reactions that produce complex hydrocarbons, which eventually settle onto the surface as tholins. These tholins give Pluto its reddish-brown hue and suggest that similar processes could be occurring on other icy bodies in the solar system, such as Titan, Saturn's largest moon. The haze also contributes to the planet's seasonal shifts and atmospheric dynamics, creating a surprisingly dynamic system for such a distant, icy world. In addition to Pluto's atmosphere, its interaction with solar wind, a stream of charged particles emitted by the Sun, provides another intriguing avenue of study. Despite its distance from the Sun, Pluto is still affected by the solar wind, which creates a tail of ionized gas trailing behind the planet. This tail is similar to the ones seen on comets, which also form due to the interaction between their gases and the solar wind. The discovery of this tail around Pluto adds another layer of complexity to the dwarf planet's environment, and suggests that even distant worlds in the Kuiper belt are not entirely isolated from the influence of the Sun. As we continue to study Pluto, its place in the broader context of the solar system becomes clearer. Pluto's unique characteristics offer a window into the diversity of planetary processes that can occur on icy worlds. For example, the discovery of nitrogen glaciers and cryovolcanoes on Pluto challenges traditional ideas about what kinds of geological activity can occur on small, cold bodies. These features demonstrate that even in the outer reaches of the solar system, where sunlight is weak and temperatures are extreme, planetary bodies can remain geologically active. The geological diversity of Pluto's surface is one of its most striking features. In addition to the glaciers of Sputnik Planitia, Pluto's surface includes towering mountains of water ice, deep canyons, and large plains covered in nitrogen and methane ices. These features suggest that Pluto has a complex and dynamic geological history, likely driven by internal heat and possibly by interactions with its largest moon, Charon. The presence of tectonic features, such as ridges and faults, indicates that Pluto's crust has been deformed over time, possibly due to the expansion and contraction of an internal ocean. The possibility of a subsurface ocean on Pluto is one of the most exciting discoveries made by the New Horizons mission. While Pluto's surface is frozen solid, there is evidence to suggest that heat from the planet's interior may be sufficient to maintain a layer of liquid water beneath the icy crust. This heat could come from the radioactive decay of elements within Pluto's core, or from tidal forces exerted by Charon. If a subsurface ocean exists on Pluto, it would likely be composed of a mixture of water, ammonia, and other volatiles, which would lower the freezing point and allow the liquid to remain stable despite the cold temperatures. The potential for liquid water on Pluto raises intriguing questions about the possibility of life on this distant world. While Pluto's surface is far too cold to support life as we know it, a subsurface ocean, insulated by a thick layer of ice, could provide a stable environment where water and organic molecules might interact. These conditions are similar to those found on other icy moons in the outer solar system, such as Europa and Enceladus, which are considered prime candidates for the search for extraterrestrial life. While the likelihood of life on Pluto is speculative, the discovery of a subsurface ocean would make it a valuable target for future astrobiological studies. The interaction between Pluto and its moons also provides important insights into the dynamics of planetary systems in the outer solar system. Charon, Pluto's largest moon, is a unique companion, as the two bodies are tidally locked, meaning they always show the same face to each other. This gravitational relationship has likely influenced the geological evolution of both bodies, and it raises interesting questions about the formation of moons in the Kuiper Belt. The smaller moons of Pluto, Styx, Nix, Kerberos, and Hydra, are thought to have formed from debris created by a giant impact, similar to how Earth's moon was formed. These moons have chaotic orbits, which are influenced by the gravitational pull of both Pluto and Charon, and their irregular shapes suggest that they may be remnants of the early solar system. Charon itself is a fascinating world, with a surface that is markedly different from Pluto's. While Pluto's surface is dominated by nitrogen and methane ices, Charon's surface is composed primarily of water ice, with large areas of reddish tholins. The presence of canyons and other tectonic features on Charon suggests that it, too, may have been geologically active in the past, possibly due to internal heat or tidal interactions with Pluto. Charon's large size relative to Pluto, it is about half the size of Pluto, and its close proximity make the Pluto-Charon system a binary system, where the two bodies orbit a common center of mass. The discovery of Pluto's moons and their unusual characteristics has opened up new avenues of research into the formation and evolution of moon systems in the outer solar system. The chaotic orbits of the smaller moons, in particular, raise questions about how these moons were captured or formed in the Kuiper Belt. Future missions to Pluto could provide more detailed observations of these moons, shedding light on their composition, history, and potential for geological activity. As our understanding of Pluto deepens, so too does our appreciation for the complexities of the outer solar system. Pluto, once thought to be a cold, dead world, has revealed itself to be a dynamic and diverse planet with a rich geological history, a tenuous atmosphere, and the potential for liquid water beneath its icy surface. Its study has provided valuable insights into the processes that govern icy worlds, both in the Kuiper Belt and beyond. The exploration of Pluto is also part of a broader effort to understand the Kuiper Belt, a vast region of the solar system that remains largely unexplored. The Kuiper Belt is home to a wide variety of icy bodies, many of which are likely similar to Pluto in size, composition, and geological history. By studying Pluto and its fellow Kuiper Belt objects, scientists hope to gain a better understanding of the processes that shape the outer solar system and the role that these distant bodies played in the solar system's formation. The New Horizons mission was the first step in this exploration, but future missions will likely build on its discoveries. There is growing interest in sending a follow-up mission to Pluto, one that could orbit the planet and provide more detailed observations of its surface, atmosphere, and moons. Such a mission could also explore other objects in the Kuiper Belt, providing new insights into the diversity of these distant worlds. Pluto's exploration is not only essential for understanding the planet itself but also for expanding our knowledge of the broader solar system. The Kuiper Belt, where Pluto resides, is a remnant of the early solar system and is thought to contain clues about its formation and evolution. Composed of icy bodies and dwarf planets, the Kuiper Belt is a region that has been largely untouched since the solar system's early days. As such, it represents a kind of cosmic time capsule, preserving materials and processes from billions of years ago. The objects within the Kuiper Belt, including Pluto, are often referred to as planetesimals, the building blocks of planets. These icy bodies never coalesced into a planet due to the gravitational influence of Neptune, which stirred up their orbits and prevented them from coming together. By studying Pluto and other Kuiper Belt objects (KBOs), scientists hope to better understand the processes that led to planet formation and the dynamics of the outer solar system. In addition to Pluto, there are several other large KBOs that are of great interest to astronomers. Eris, for example, is slightly smaller than Pluto but more massive, and its discovery in 2005 was one of the key events that led to the reclassification of Pluto as a dwarf planet. Like Pluto, Eris has a highly elliptical orbit, and its surface is covered in a thin layer of methane ice. Other large KBOs, such as Haumea and Makemake, also share similarities with Pluto and offer valuable insights into the diversity of objects in the Kuiper Belt. One of the most intriguing aspects of the Kuiper Belt is the possibility that it contains objects that have never been observed before. The region is so vast and distant that many of its inhabitants remain undiscovered. Some scientists believe that there could be larger, more distant objects lurking in the far reaches of the solar system, including the hypothetical Planet 9, a giant planet that is thought to be influencing the orbits of several distant KBOs. While Planet 9 has yet to be directly observed, its existence is inferred from the unusual orbits of these objects, which suggests that they are being gravitationally perturbed by a massive, unseen body. The search for Planet 9 and other distant objects in the Kuiper Belt is ongoing, and new discoveries could reshape our understanding of the outer solar system. In many ways, the exploration of Pluto and the Kuiper Belt is analogous to the early exploration of the asteroid belt between Mars and Jupiter. Just as the study of asteroids revealed important clues about the early solar system, the study of KBOs promises to unlock new secrets about the formation and evolution of our cosmic neighborhood. As we continue to explore Pluto and the Kuiper Belt, it is worth considering the broader implications of these discoveries for planetary science and astrobiology. Pluto, with its potential subsurface ocean and complex geology, challenges our traditional notions of what makes a planet habitable. While Pluto is far too cold to support life on its surface, the possibility of liquid water beneath its icy crust raises intriguing questions about the potential for life in the outer solar system. Astrobiologists are particularly interested in the idea of life existing in subsurface oceans on icy worlds, as these environments could provide the necessary conditions for life to thrive. The discovery of hydrothermal vents on Earth's ocean floor, where life thrives in complete darkness and extreme conditions, has expanded our understanding of the types of environments that could support life. Similar conditions could exist on Pluto or other icy worlds in the Kuiper Belt, where heat from internal sources, such as radioactive decay or tidal forces, could create liquid water environments that are protected from the harsh conditions of the surface. While the likelihood of finding life on Pluto is remote, the study of icy worlds in the outer solar system could help us better understand the potential for life on other planets and moons. Europa, one of Jupiter's moons, and Enceladus, one of Saturn's moons, are considered prime candidates for the search for extraterrestrial life due to their subsurface oceans and the presence of organic molecules. The exploration of Pluto and the Kuiper Belt adds another dimension to this search, as it expands the range of environments that could potentially support life. Pluto's exploration also has important implications for the study of exoplanets, planets that orbit stars outside our solar system. Many of the exoplanets that have been discovered to date are icy, distant worlds that share similarities with Pluto and other KBOs. By studying Pluto, We can gain insights into the types of processes that may be occurring on these distant exoplanets, helping us to better understand their potential for habitability. In addition to its scientific significance, Pluto holds a special place in the hearts of many people around the world. The public's fascination with Pluto is partly due to its status as an underdog planet, once relegated to the farthest reaches of the solar system, and then demoted from planetary status. However, Pluto's reclassification as a dwarf planet has not diminished its allure. In fact, the New Horizons mission reignited interest in Pluto and showcased its unique characteristics, capturing the imagination of millions. The debate over Pluto's planetary status also highlights the evolving nature of science. As our understanding of the universe expands, so too do our definitions and classifications. The decision to reclassify Pluto was based on new discoveries about the diversity of objects in the Kuiper Belt, as well as a better understanding of what constitutes a planet. While some people may lament Pluto's demotion, the scientific community views it as a reflection of our growing knowledge of the solar system. In many ways, Pluto's story is a testament to the power of exploration and discovery. From its initial discovery by Clyde Tombaugh in 1930 to the groundbreaking observations made by New Horizons, Pluto has continually surprised and intrigued scientists. Each new discovery about Pluto challenges our preconceived notions about the solar system and forces us to rethink what we know about planetary formation, geology, and the potential for life beyond Earth. The exploration of Pluto is far from over, and future missions to the dwarf planet will likely reveal even more surprises. The possibility of sending an orbiter to Pluto has been discussed, as such a mission would provide much more detailed observations than the flyby conducted by New Horizons. An orbiter could map Pluto's surface in high resolution, study its atmosphere in greater detail, and search for signs of subsurface oceans. Such a mission would also allow for extended observations of Pluto's moons, providing new insights into their formation and evolution. In addition to a potential Pluto orbiter, future missions could target other objects in the Kuiper Belt, building on the success of New Horizons. By studying a variety of KBOs, scientists hope to gain a more comprehensive understanding of the outer solar system and the processes that shaped it. The exploration of the Kuiper Belt is still in its early stages, and there is much more to discover about this distant region of space. As we look to the future, it is clear that Pluto will continue to be a focus of scientific study and public interest. Its unique combination of characteristics, its dynamic geology, tenuous atmosphere, potential subsurface ocean, and complex moon system, make it one of the most fascinating objects in the solar system. The discoveries made by New Horizons have only scratched the surface of what Pluto has to offer, and future missions will undoubtedly reveal even more about this enigmatic world. In the grand scheme of the solar system, Pluto may be small and distant, but its significance is undeniable. It serves as a reminder that even the most remote and seemingly inhospitable places can hold valuable clues about the nature of the universe. Pluto's exploration has expanded our understanding of planetary science and opened new avenues of research into the outer solar system, Kuiper Belt objects, and the potential for life in extreme environments. As humanity continues to explore the solar system and beyond, Pluto stands as a symbol of the unyielding curiosity and determination that drives scientific discovery. Its journey from a faint point of light in the night sky to a world of towering ice mountains, nitrogen glaciers, and potential oceans is a testament to the power of exploration. And as we continue to push the boundaries of what is known, Pluto will remain a beacon of mystery and wonder in the distant reaches of the solar system. The significance of Pluto's exploration extends beyond just our solar system. Its discovery, and subsequent reclassification, sparked a broader conversation about what it means to be a planet, and more generally, about the human endeavor to categorize and understand the universe. This debate brought to light the limitations of our definitions and the ways in which scientific discovery forces us to reevaluate those frameworks. The discussion surrounding Pluto reminds us that scientific progress is not a static journey, it is fluid, with definitions and concepts that evolve as new information is uncovered. When Pluto was first discovered in 1930, it was celebrated as the ninth planet in our solar system, filling a perceived gap in the outer reaches of the solar system. For decades, students were taught that our solar system consisted of 9 planets, with Pluto marking the distant edge. However, the discovery of other small, icy bodies in the Kuiper Belt during the 1990s and 2000s forced astronomers to reconsider Pluto's place among the planets. As more objects similar to Pluto were found, such as Eris, Haumea, and Makemake, it became clear that Pluto was not unique in its size or location. This realization culminated in the controversial 2006 decision by the International Astronomical Union, IU, to reclassify Pluto as a dwarf planet. To qualify as a planet under the new definition, an object must orbit the Sun, be massive enough for its gravity to shape it into a nearly round shape, and clear its orbit of other debris. While Pluto meets the first 2 criteria, it fails to clear its orbit, as it shares its space with other objects in the Kuiper Belt. This reclassification sparked an intense public debate, with many people feeling an emotional attachment to Pluto as the 9th planet. For them, Pluto's demotion was more than just a technicality. It was a challenge to their perception of the solar system, which had been shaped by decades of education and popular culture. The debate surrounding Pluto's status as a planet also raised important questions about how we define other astronomical objects. The IU's definition of a planet was designed to reflect our improved understanding of the solar system, but it also highlighted the challenges of creating a universal classification system that can accommodate new discoveries. Some astronomers have argued that the definition should be broadened to include a wider variety of objects, while others believe that it is essential to maintain strict criteria to preserve the distinction between planets and other celestial bodies. The public's fascination with Pluto's reclassification underscores the deep connection that many people feel to the solar system and its celestial inhabitants. Pluto, with its distant and mysterious nature, had long captured the imagination of astronomers and the general public alike. Its demotion to a dwarf planet did little to diminish its appeal, as evidenced by the immense excitement surrounding the New Horizons mission in 2015. This mission not only provided unprecedented insights into Pluto, but also reignited public interest in space exploration and the ongoing quest to understand the outer reaches of the solar system. The exploration of Pluto, both scientifically and culturally, reflects humanity's broader desire to explore and understand the universe. It speaks to our innate curiosity and our drive to push the boundaries of knowledge. Whether Pluto is classified as a planet or a dwarf planet, its role in expanding our understanding of the solar system is undeniable. The data collected by New Horizons transformed Pluto from a distant, icy body into a dynamic world with complex geological features, a tenuous atmosphere, and potentially even an underground ocean. These discoveries have sparked new lines of inquiry and have inspired future missions to explore the outer solar system in greater detail. Pluto's exploration is also a testament to the power of human ingenuity and perseverance. Sending a spacecraft to Pluto required overcoming immense technical challenges, as the dwarf planet is located nearly 4 billion miles from Earth. The journey took nearly a decade, and the spacecraft had to navigate through the outer reaches of the solar system, where sunlight is weak and the temperatures are frigid. Despite these challenges, New Horizons successfully reached Pluto, and the data it collected provided a wealth of information that has reshaped our understanding of the solar system. The success of New Horizons has inspired a new generation of scientists and engineers to pursue careers in space exploration. It has also demonstrated the importance of investing in long-term, ambitious missions that push the boundaries of what is possible. While it took nearly a decade for New Horizons to reach Pluto, the insights gained from the mission have proven invaluable, and they will continue to shape our understanding of the solar system for years to come. Looking forward, there are still many unanswered questions about Pluto and the Kuiper Belt. Future missions could provide more detailed information about Pluto's atmosphere, surface composition, and potential subsurface ocean. One of the most intriguing questions is whether Pluto's internal heat is sufficient to sustain a liquid ocean beneath its icy crust. If such an ocean exists, it would have profound implications for the potential for life in the outer solar system. In addition, continued exploration of the Kuiper Belt could reveal new objects and phenomena that challenge our current understanding of planetary formation and evolution. The exploration of Pluto and the Kuiper Belt is part of a broader effort to understand the outer solar system, which remains one of the most mysterious and least explored regions of our cosmic neighborhood. The outer solar system is home to many fascinating and enigmatic objects, including gas giants, icy moons, and distant dwarf planets like Pluto. By studying these objects, scientists hope to gain insights into the early history of the solar system and the processes that led to the formation of planets and other celestial bodies. The outer solar system also holds important clues about the origins of life. Many of the moons of the outer planets, such as Europa and Enceladus, are believed to harbor subsurface oceans that could potentially support life. These icy moons, along with Pluto and other objects in the Kuiper Belt, represent a new frontier in the search for life beyond Earth. While the harsh conditions of the outer solar system make it unlikely that life could exist on the surface of these objects, the possibility of subsurface oceans provides a tantalizing hint that life could exist in environments far different from those found on Earth. In the broader context of space exploration, Pluto serves as a reminder of the vastness and diversity of the solar system. As we continue to explore the outer reaches of our cosmic neighborhood, we are likely to encounter new and unexpected phenomena that challenge our current understanding of the universe. Each new discovery adds another piece to the puzzle, bringing us closer to a comprehensive understanding of the solar system and its many mysteries. Ultimately, the exploration of Pluto and the Kuiper Belt is not just about understanding these distant objects, it is about understanding our place in the universe. The discoveries made by New Horizons and other missions to the outer solar system have expanded our knowledge of planetary science, astrobiology, and the dynamics of celestial bodies. They have also sparked a renewed sense of wonder and curiosity about the cosmos, reminding us that there is still much to learn and discover. As we look to the future, Pluto will undoubtedly continue to play a central role in our quest to understand the solar system. Its unique characteristics, combined with its status as a dwarf planet in the Kuiper Belt, make it a valuable subject of study for scientists and astronomers. Future missions to Pluto and the Kuiper Belt will likely reveal even more surprises, deepening our understanding of the outer solar system and its many mysteries. In conclusion, Pluto's exploration represents one of the most significant milestones in planetary science and space exploration. From its initial discovery in 1930 to the groundbreaking observations made by New Horizons, Pluto has continually challenged our understanding of the solar system and forced us to rethink our definitions and classifications. As we continue to explore Pluto and the Kuiper Belt, we are likely to uncover new insights into the formation and evolution of planets, the potential for life in extreme environments, and the broader dynamics of the outer solar system. Pluto may be small and distant, but its significance is undeniable, and its exploration will continue to inspire future generations of scientists, engineers, and explorers. The significance of Pluto extends even further when considering its role in shaping our understanding of planetary science. As more observations and data are gathered, not just about Pluto but also about other Kuiper Belt objects, KBOs, a more detailed and refined picture of the outer reaches of the solar system emerges. KBOs, including Pluto, represent remnants from the solar system's early history. They are like time capsules, preserving information about the primordial material that formed the planets. By studying these objects, scientists can gain insights into the processes that govern planetary formation and the migration of celestial bodies during the solar system's infancy. In the past, the solar system was thought to be more rigid in structure, with planets and other bodies occupying more or less fixed orbits. However, as scientists have studied the Kuiper Belt and other distant regions, it has become clear that the early solar system was much more dynamic. For instance, models suggest that Neptune may have migrated outward from its original position closer to the Sun, which could explain the presence of the Kuiper Belt objects in their current orbits. Such planetary migrations would have caused considerable disruptions in the orbits of smaller bodies like Pluto, potentially ejecting some objects out of the solar system while trapping others in stable orbits within the Kuiper Belt. This concept of planetary migration has transformed our understanding of not only Pluto, but also of the formation and evolution of the entire solar system. The idea that planets like Neptune and even Jupiter may have migrated significantly from their original positions during the solar system's early history has led scientists to revisit theories about how planets form and evolve over time. It also raises questions about whether such migrations could occur in other star systems, and whether similar processes might govern the formation of exoplanets. Pluto's icy surface, composed of nitrogen, methane, and carbon monoxide, provides an intriguing window into the chemistry of the outer solar system. The presence of methane ice, in particular, is noteworthy because methane is a compound that can react with other elements to form more complex organic molecules, which are the building blocks of life. While there is no evidence to suggest that life exists on Pluto, the presence of methane on its surface, along with the potential for subsurface oceans, raises interesting possibilities about the chemical processes that might occur in such environments. One of the most unexpected discoveries made by New Horizons was the complexity of Pluto's surface. Scientists had expected Pluto to be a relatively uniform, frozen world, but the data returned by the spacecraft revealed a dynamic and geologically diverse surface. Pluto has towering mountains of water ice, vast plains of nitrogen ice, and even evidence of possible cryovolcanism, where icy materials are erupted onto the surface. One of the most striking features is Sputnik Planitia, a large, heart-shaped plain of nitrogen ice that appears to be relatively young and geologically active. This suggests that Pluto, despite its small size and distance from the Sun, may have some form of internal heat that drives geological activity. The source of this internal heat remains a subject of debate. One possibility is that radioactive decay within Pluto's core generates enough heat to power the geological processes observed on its surface. Another theory suggests that Pluto's interaction with its largest moon, Charon, could create tidal forces that generate heat within the dwarf planet's interior. However, more data is needed to determine which processes are responsible for Pluto's geological activity, and future missions to the Kuiper Belt could help to shed light on this mystery. Charon, Pluto's largest moon, is also a fascinating object of study. It is so large relative to Pluto that the two objects are sometimes referred to as a binary system, meaning that they orbit a common center of gravity located between them. This relationship is unique in the solar system and has provided scientists with valuable insights into the formation and evolution of planetary systems. Charon's surface is covered in water ice, and like Pluto, it shows evidence of geological activity. The discovery of large chasms and fractures on Charon's surface suggests that it may have experienced tectonic forces, possibly driven by internal heat or past tidal interactions with Pluto. The Pluto-Charon system also offers a glimpse into how binary objects form and interact. Binary systems are not uncommon in the universe, and understanding the dynamics of the Pluto-Charon system can provide important clues about the formation of binary stars and other binary systems in distant star systems. Additionally, the fact that Charon and Pluto are tidally locked to each other, meaning that the same side of each body always faces the other, creates unique conditions for studying the effects of tidal forces on planetary bodies. Beyond Pluto and Charon, the broader Kuiper Belt is home to thousands of small icy bodies, many of which remain largely unexplored. These objects vary widely in size, composition, and orbit, and they represent some of the oldest and most pristine material in the solar system. Some Kuiper Belt objects, like Eris, are similar in size to Pluto, while others are much smaller and more irregularly shaped. Studying these objects can provide valuable insights into the diversity of planetary bodies that exist in the outer solar system and help to refine our understanding of the processes that govern planetary formation. One of the most exciting prospects for future exploration is the possibility of sending additional missions to the Kuiper Belt to study these distant objects in greater detail. While New Horizons provided a wealth of information about Pluto and its moons, there is still much to learn about the broader population of Kuiper Belt objects. Future missions could be equipped with more advanced instruments to study the surface composition, geology, and atmospheres of these objects, as well as their potential for harboring subsurface oceans or other interesting features. In addition to robotic missions, there is also growing interest in the possibility of sending crewed missions to the outer solar system. While such missions are likely decades away, advances in space travel technology could one day make it possible for humans to visit distant objects like Pluto. Such missions would represent a significant leap forward in our ability to explore the outer reaches of the solar system and could provide valuable data that is difficult to obtain with robotic spacecraft alone. As our exploration of the Kuiper Belt and beyond continues, Pluto will remain a central figure in our quest to understand the solar system. Its complex geology, dynamic atmosphere, and intriguing potential for subsurface oceans make it an object of enduring scientific interest. Moreover, Pluto's role in the broader context of planetary science, both as a member of the Kuiper Belt and as a subject of the ongoing debate over planetary classification, ensures that it will continue to captivate scientists and the public alike. The future of Pluto research is bright, with many exciting possibilities on the horizon. Whether through future spacecraft missions, new telescopic observations, or advances in our understanding of planetary science, Pluto will remain a key player in our ongoing exploration of the outer solar system. Its unique characteristics, combined with its status as a dwarf planet in the Kuiper Belt, make it a valuable subject of study for generations of scientists to come. Pluto may be small and distant, but its significance is vast. It has reshaped our understanding of the solar system, challenged our definitions of planets, and inspired new lines of inquiry about the nature of the outer solar system. As we continue to explore this distant world and its neighbors in the Kuiper Belt, we are reminded of the boundless possibilities that await us in the vast, unexplored regions of the cosmos. The exploration of Pluto is just the beginning, and the discoveries we make in the years to come will undoubtedly deepen our understanding of the universe and our place within it. Pluto's discovery in 1930 by astronomer Clyde Tombaugh at the Lowell Observatory was a monumental achievement in the field of astronomy. For decades, it stood as the ninth planet of the solar system, adding to the grandeur of our celestial neighborhood. The discovery of Pluto sparked a sense of wonder and curiosity among scientists and the public alike, as it was the first object discovered in what we now recognize as the Kuiper Belt, a region beyond Neptune filled with icy bodies. While its planetary status has changed, Pluto's legacy in astronomical history remains deeply significant. In the early days after Pluto's discovery, much of what we knew about this distant world was based on limited telescopic observations. For many years, Pluto remained an enigma, as its great distance from Earth made it difficult to observe in detail. However, its discovery opened up a new frontier in planetary science, prompting astronomers to speculate about what other objects might exist in the outer solar system. Pluto's position, far beyond the gas giants, also led to questions about the nature of planets and how the solar system was structured. During the mid-20th century, new observations of Pluto revealed some of its more peculiar traits. Its orbit, for instance, was found to be highly elliptical and inclined compared to the orbits of the other planets, causing it to cross Neptune's orbit at times. This odd orbit fueled debates about Pluto's origin and its relationship to the broader solar system. Pluto's small size also raised questions about its classification, as it was much smaller than the other planets, and even smaller than some of the moons in the solar system. In 1978, the discovery of Charon, Pluto's largest moon, by astronomer James Christie added another layer to our understanding of Pluto. Charon's discovery was significant because it allowed astronomers to measure Pluto's mass more accurately. This revealed that Pluto was much smaller and less massive than previously thought. The Pluto-Charon system also presented a unique dynamic, as the two bodies are tidally locked to one another, meaning they always show the same face to each other. This discovery further highlighted Pluto's distinct characteristics and deepened the mystery surrounding it. The discoveries didn't stop there. In the years following the identification of Charon, astronomers found additional moons orbiting Pluto, including Nix and Hydra in 2005, and later Kerberos and Styx. These discoveries demonstrated that Pluto had a more complex system than initially thought, leading scientists to rethink their understanding of small, distant objects in the outer solar system. Pluto's system of moons, coupled with its relationship to the Kuiper Belt, made it a unique and intriguing subject for study. The decision to reclassify Pluto as a dwarf planet in 2006 by the International Astronomical Union (IAU) was met with controversy and emotional responses from the public. The decision was based on new criteria for classifying planets, one of which was that a planet must have cleared its orbit of other debris. Since Pluto shares its orbital zone with other Kuiper Belt objects, it no longer met the criteria to be considered a full-fledged planet. This reclassification reflected a growing understanding of the diversity of objects in the outer solar system, but it also led to a period of reflection about what it means to be a planet. While Pluto's demotion was seen as a loss by many, it also opened the door to new lines of inquiry. Astronomers began to focus more attention on the Kuiper Belt and the many objects it contains, leading to the discovery of other dwarf planets like Eris, Haumea, and Makemake. These discoveries revealed that Pluto was not an isolated object but rather part of a larger population of distant icy bodies, each with its own unique characteristics. The recognition of these objects as dwarf planets provided a more nuanced understanding of the outer solar system. The New Horizons mission, which launched in 2006 and flew by Pluto in 2015, was a game-changer in our understanding of this distant world. It marked the first time that a spacecraft had visited Pluto, providing humanity with its first close-up images and data of the dwarf planet and its moons. The images sent back by New Horizons were nothing short of astonishing. They revealed a world far more complex and active than scientists had imagined. One of the most surprising discoveries was the varied and dynamic nature of Pluto's surface. Prior to New Horizons, Pluto was thought to be a relatively static, icy world. However, the spacecraft's data revealed vast plains of nitrogen ice, towering mountains made of water ice, and evidence of geological activity. Perhaps the most iconic feature revealed by New Horizons was Sputnik Planitia, a heart-shaped region of nitrogen ice that appears to be geologically young, with no impact craters visible on its surface. This suggests that Pluto has been reshaped by internal processes relatively recently in its history. The presence of such dynamic features on Pluto's surface was unexpected, as the dwarf planet was thought to be too small and cold to have retained enough internal heat to drive geological activity. The discovery of these features has led scientists to speculate about the possible sources of Pluto's internal heat. One possibility is the radioactive decay of elements within Pluto's core, which could generate enough heat to drive the movement of ices on its surface. Another possibility is that Pluto's interaction with Charon may create tidal forces that generate heat within its interior. New Horizons also revealed the complex and intriguing atmosphere of Pluto. Unlike most objects in the Kuiper Belt, Pluto has a thin atmosphere composed mainly of nitrogen, with traces of methane and carbon monoxide. The atmosphere is highly tenuous and is in a constant state of change as Pluto moves along its elliptical orbit. During its closest approach to the Sun, Pluto's surface warms slightly, causing some of the nitrogen ice to sublimate and form a thin atmosphere. As Pluto moves farther from the Sun, the atmosphere cools and freezes back onto the surface. This cyclical process creates a dynamic atmosphere that is constantly evolving over the course of Pluto's long year. One of the most remarkable findings from New Horizons was the detection of haze layers in Pluto's atmosphere. These haze layers are likely composed of complex organic molecules that form as a result of interactions between sunlight and the methane in Pluto's atmosphere. The presence of these haze layers suggests that Pluto's atmosphere is more chemically active than previously thought, and may provide clues about the processes that shape the atmospheres of other distant objects in the solar system. Pluto's atmosphere also exhibits surprising interactions with the solar wind, the stream of charged particles that flows from the Sun. As the solar wind reaches Pluto, it interacts with the dwarf planet's atmosphere, creating a tail of ionized gas that stretches behind Pluto. This interaction is similar to the way the solar wind interacts with comets, leading scientists to refer to Pluto as a hybrid object that shares characteristics of both planets and comets. The discovery of Pluto's atmosphere, along with its varied surface features, has challenged previous assumptions about what small, icy worlds in the outer solar system are like. It has forced scientists to reconsider the complexity of these distant objects, and has raised new questions about the processes that shape them. Pluto's status as a dwarf planet in the Kuiper belt also provides a unique opportunity to study the outermost regions of the solar system and to learn more about the early history of planetary formation. The continued exploration of Pluto and the Kuiper belt has implications beyond just understanding Pluto itself. It offers insights into the formation and evolution of our solar system. The objects in the Kuiper belt are believed to be remnants from the solar system's early history, preserving clues about the conditions that existed during its formation over 4.5 billion years ago. Studying Pluto, therefore, allows scientists to piece together the story of how our solar system came to be and how the various planets and dwarf planets evolved over time. One of the exciting prospects of studying Pluto is the potential to discover more about the possibility of life beyond Earth. While Pluto's surface conditions are extremely harsh and far from conducive to life as we know it, the discovery of subsurface oceans on other icy bodies, such as Europa and Enceladus, has reignited interest in the possibility that life might exist in unexpected places. Some scientists theorize that Pluto could harbor a subsurface ocean, kept warm by residual heat from its formation or internal tidal forces generated by its interaction with Charon. The idea of a hidden ocean beneath Pluto's icy shell raises tantalizing questions about the potential for life in environments previously thought to be too extreme. As we move into a new era of planetary exploration, the legacy of Pluto is continuing to evolve. The interest in Kuiper belt objects (KBOs) has surged, with various missions being planned to explore these distant worlds further. For instance, the upcoming mission called Lucy will fly by several KBOs and is designed to study these ancient objects to better understand the solar system's formation. Additionally, NASA's New Horizons mission is being considered for further extensions, potentially targeting additional KBOs in the years to come. Such missions could provide invaluable data and enrich our understanding of the early solar system's evolution. The significance of Pluto is not merely scientific. It has also captured the imagination of the public. Pluto's reclassification in 2006 ignited a passionate debate over what constitutes a planet, leading to discussions about the nature of scientific classification itself. This debate resonates beyond astronomy and into broader cultural discussions about identity and categorization. The emotional connection many people feel toward Pluto stems from its status as the first object discovered in the Kuiper belt and the nostalgia associated with its long-standing position as the 9th planet of the solar system. The story of Pluto is emblematic of the broader narrative of scientific discovery. As new technologies and methods of exploration become available, our understanding of celestial objects continues to deepen and evolve. Each new discovery, whether it is the complex surface of Pluto, the dynamics of its atmosphere, or the presence of its moons, adds layers to the story we tell about our solar system. As we delve deeper into these mysteries, we are reminded that the universe is a vast and dynamic place, rich with history and complexity. The cultural impact of Pluto extends beyond scientific circles. It has been embraced by artists, writers, and filmmakers. Pluto has become a symbol of exploration and curiosity, representing humanity's desire to understand the universe and our place within it. The story of Pluto has been woven into literature, movies, and popular culture, capturing the imaginations of generations. It serves as a reminder of the wonders of space and the unending quest for knowledge that drives humanity. As we consider the future of planetary exploration, it is essential to recognize the role of public interest and engagement in shaping our understanding of the cosmos. The story of Pluto illustrates how science is not just a solitary pursuit. It thrives on collaboration and dialogue between scientists, educators, and the public. Educational initiatives and outreach programs that share the discoveries of missions like New Horizons help to foster a sense of connection to the universe and inspire future generations of astronomers and explorers. In conclusion, the journey of understanding Pluto has been a remarkable one. From its initial discovery to its reclassification as a dwarf planet, Pluto has challenged our notions of what constitutes a planet and has opened new avenues for exploration. The data returned by the New Horizons mission has fundamentally altered our understanding of this distant world and has sparked renewed interest in the Kuiper Belt and the objects that reside there. As we continue to study Pluto and the broader solar system, we are reminded of the endless possibilities that await us in the cosmos. The complexities of Pluto, its atmosphere, surface features, and relationship with its moons, provide a glimpse into the dynamic processes that govern not only this dwarf planet but also other celestial bodies. As new missions are planned, and our technology continues to advance, we can anticipate further revelations about Pluto and the Kuiper Belt, enriching our knowledge of the solar system and expanding our understanding of where we fit within the grand tapestry of the universe. With every new discovery, we draw closer to answering fundamental questions about the nature of our solar system and the potential for life beyond Earth. Pluto's journey is far from over. It remains a vibrant and active field of study that will undoubtedly yield more surprises in the years to come. As we look to the stars and contemplate our place in the universe, Pluto serves as a testament to the spirit of exploration and the unyielding quest for knowledge that defines humanity. The story of Pluto is not just a tale of a distant dwarf planet. It is a reflection of our collective curiosity and our desire to understand the mysteries of the cosmos. As we delve deeper into the intricacies of Pluto, we uncover not only its physical characteristics but also the broader implications of its existence within the solar system. The study of Pluto has the potential to reshape our understanding of planetary science and the formation of celestial bodies. Its diverse geology and unique atmospheric dynamics challenge long-held assumptions about the conditions necessary for geological activity and atmospheres to exist in the outer reaches of the solar system. One of the most compelling aspects of Pluto's story is how it has inspired scientific inquiry and innovation. The challenges posed by its distance and the harsh environment of the Kuiper Belt necessitated advancements in spacecraft technology, imaging systems, and data analysis techniques. The New Horizons mission, for example, employed a suite of sophisticated instruments designed to capture high-resolution images and gather detailed data about Pluto's surface composition, atmosphere, and geological features. This mission exemplifies how ambitious space exploration can drive technological advancements that ultimately benefit multiple fields, from materials science to remote sensing. Pluto's surface, which features a mixture of nitrogen ice, methane ice, and carbon monoxide, offers insights into the processes that shape icy bodies in the outer solar system. The complex interactions between these substances, influenced by temperature fluctuations and solar radiation, create a rich tapestry of geological features. Observations from New Horizons revealed large, rugged mountains made of water ice, which suggests tectonic activity, something previously thought to be exclusive to larger planets. The presence of these mountains indicates that Pluto has a geologically dynamic history, challenging the notion that small celestial bodies are inert and static. The discovery of vast plains like Sputnik Planitia raises questions about the climatic history of Pluto. The interplay between its thin atmosphere and surface conditions is a topic of ongoing research. As scientists analyze the data from New Horizons, they are piecing together the puzzle of how Pluto's climate has changed over time and how it interacts with the solar wind and cosmic radiation. These studies may provide valuable lessons applicable to other icy bodies in the solar system and beyond. Understanding Pluto's internal structure is another crucial aspect of ongoing research. While New Horizons provided a wealth of surface data, scientists are now focused on constructing models of Pluto's interior. The idea of a subsurface ocean, similar to those hypothesized on moons like Europa and Enceladus, adds a tantalizing dimension to our understanding of potential habitability. If Pluto possesses an ocean beneath its icy crust, it could open the door to exploring whether life might exist in extreme environments beyond Earth. In the broader context of the solar system, Pluto serves as a representative of the Kuiper Belt, a region that is rich in diverse celestial objects. The Kuiper Belt is home to thousands of icy bodies, and its study has become increasingly important in the field of planetary science. The discovery of objects like Eris, Haumea, and Makemake has led to a reevaluation of what defines a planet, and has highlighted the importance of understanding these distant worlds in the context of the solar system's history. The insights gained from studying Pluto and other KBOs can illuminate the processes that governed the early solar system and provide context for the formation of the planets we see today. In addition to its scientific significance, Pluto also raises philosophical questions about classification and identity in science. The debate surrounding its reclassification as a dwarf planet serves as a reminder that scientific definitions can evolve as our understanding deepens. This ongoing dialogue about what constitutes a planet or a dwarf planet is emblematic of the scientific process itself, an ever-evolving quest for knowledge that is grounded in observation, exploration, and discourse. As public interest in Pluto and the Kuiper Belt grows, it reflects a broader fascination with space exploration and the unknown. The emotional connection many people feel towards Pluto is tied to its status as a former planet, and its representation of the quest for discovery. Pluto's reclassification ignited discussions not just about astronomy but also about how we perceive and categorize the natural world. This blend of science and culture enriches our understanding of both and highlights the importance of engaging the public in scientific discourse. Educational initiatives aimed at increasing awareness of Pluto and the Kuiper Belt play a vital role in fostering interest in planetary science. Schools and universities are beginning to incorporate planetary science into their curricula, emphasizing the importance of exploration and discovery. The availability of data and images from missions like New Horizons allows educators to inspire the next generation of scientists and explorers by bringing the wonders of the universe closer to home. As we look toward the future, the story of Pluto is far from complete. With ongoing advancements in technology and upcoming missions designed to explore other KBOs, we can expect to uncover more about this fascinating region of the solar system. Future telescopes and missions will enable astronomers to probe deeper into the mysteries of the Kuiper Belt, seeking to understand its formation and the processes that govern the behavior of its inhabitants. Projects like the European Space Agency's JUICE mission and the upcoming NASA missions, such as the planned missions to study Trojan asteroids, are poised to expand our understanding of the outer solar system. The excitement surrounding the exploration of the Kuiper Belt and the discovery of new objects continues to inspire awe and curiosity. As we study these distant worlds, we gain a better understanding of our own planet and the unique position it occupies within the solar system. The story of Pluto, once relegated to the margins of planetary science, is now at the forefront of our quest to comprehend the cosmos and our place within it. Moreover, the exploration of Pluto and its region prompts us to think critically about the nature of exploration itself. As we send spacecraft to the far reaches of the solar system, we confront questions about the ethics of exploration and the responsibilities that come with understanding these distant worlds. The knowledge we gain carries with it an obligation to consider how our actions may impact not only our own planet but also the other celestial bodies we explore. The legacy of Pluto is one of curiosity and discovery, and it compels us to approach the unknown with both wonder and responsibility. Ultimately, Pluto remains a symbol of exploration and the unyielding human spirit. Its journey from a celebrated planet to a reclassified dwarf planet has only enriched its narrative, highlighting the complexities of scientific inquiry and the ever-evolving nature of knowledge. As we continue to explore the outer solar system, Pluto will undoubtedly play a significant role in our quest to understand not just our solar system but the universe at large. Pluto is not merely a distant, icy world. It represents the essence of scientific discovery, an embodiment of humanity's relentless pursuit of knowledge and the mysteries that lie beyond our planet. The exploration of Pluto and its unique characteristics serves as a reminder of the complexity and diversity of the solar system, as well as the ever-present questions that drive scientific inquiry. With each new discovery, we draw closer to understanding our place in the universe, and Pluto, with its rich history and intriguing features, will undoubtedly continue to captivate our imaginations and inspire future generations of explorers. Continuing the discussion of Pluto and its significance in our understanding of the solar system, it's essential to recognize the role that international collaboration plays in space exploration. Missions like New Horizons were not only American endeavors but involved partnerships and contributions from scientists and institutions around the globe. This collaborative spirit is vital for tackling the immense challenges of interplanetary exploration and underscores the importance of a united effort in the pursuit of knowledge. The sharing of data from missions like New Horizons exemplifies this collaborative approach. Researchers from various countries have access to the wealth of information gathered during the flyby, allowing for diverse analyses and interpretations of the data. This open exchange of knowledge is crucial for advancing planetary science and fostering a global community dedicated to understanding our place in the cosmos. As different teams of scientists examine the findings from New Horizons, new insights emerge, providing a more comprehensive understanding of Pluto and its environment. Moreover, the success of the New Horizons mission has sparked renewed interest in the Kuiper Belt, inspiring new proposals for missions to explore other KBOs. For instance, concepts like the KBO Explorer, KBOE, and the far-off potential mission to visit the recently discovered KBOs offer exciting prospects for future exploration. Each mission has the potential to uncover new features, atmospheres, and compositions of these distant worlds, thereby enriching our understanding of the solar system's outer regions. The advancements in technology that enabled the success of New Horizons will also pave the way for future missions. Innovations in propulsion systems, imaging technologies, and data transmission methods are vital for exploring the distant reaches of the solar system more effectively. The lessons learned from the challenges faced during the New Horizons mission are invaluable for planning future endeavors, ensuring that the exploration of Pluto and similar objects continues to yield rich scientific returns. In addition to the technological advancements, the quest to understand Pluto has brought to light the significance of astrobiology, the study of the potential for life beyond Earth. As scientists investigate the possibility of subsurface oceans on icy bodies, the implications of these findings extend to the search for extraterrestrial life. While Pluto itself may not harbor life, the discovery of similar features on other celestial bodies suggests that life could exist in environments previously thought to be inhospitable. The interest in astrobiology and the potential for life beyond Earth ties into the larger narrative of humanity's quest for knowledge. Each discovery, whether it concerns Pluto or another celestial body, deepens our understanding of life's possibilities in the universe and encourages ongoing exploration. The search for life beyond our planet is one of the most profound questions facing humanity, and the study of distant worlds like Pluto and the KBOs provides critical insights into the conditions that may foster life. Another important aspect of Pluto's story is the cultural and emotional connection that many people have with this distant world. The debate over its planetary status reflects broader themes in society regarding classification, identity, and belonging. For many, Pluto symbolizes the spirit of exploration and curiosity that drives scientific inquiry. The outpouring of sentiment regarding Pluto's reclassification underscores how deeply intertwined our scientific understanding is with our cultural narratives. The public's fascination with Pluto can also be attributed to its representation in popular media and literature. From documentaries to children's books, Pluto has become a cultural icon, serving as a gateway for introducing complex scientific concepts to a broader audience. This engagement helps demystify space science, making it more accessible to people of all ages. The more we share the wonders of the universe, the more likely we are to inspire future generations of scientists, engineers, and explorers. As we contemplate the future of our exploration of the outer solar system, it's essential to recognize the role that education and outreach play in shaping public interest. The success of missions like New Horizons not only advances scientific knowledge, but also ignites a passion for exploration in young minds. Educational programs that emphasize STEM, science, technology, engineering, and mathematics can harness this enthusiasm, fostering a new generation of explorers who will continue the quest to understand our universe. Furthermore, the legacy of Pluto extends beyond its status as a celestial body. It serves as a reminder of the importance of scientific literacy and public engagement in shaping our understanding of the cosmos. The story of Pluto illustrates that science is not an isolated endeavor but a collective journey that involves curiosity, inquiry, and dialogue. As we explore the universe, we must continue to embrace the spirit of collaboration and engagement that characterizes scientific exploration. In recent years, there has been a renewed interest in the search for exoplanets. planets that orbit stars outside our solar system. The discoveries of thousands of exoplanets have expanded our understanding of planetary formation and the diversity of worlds that exist beyond our own. The knowledge gained from studying distant planets can inform our understanding of Pluto and the Kuiper Belt, offering insights into the processes that shape planetary systems. As we strive to understand our solar system and beyond, Pluto remains a focal point for scientific inquiry. The complexities of its geology, atmosphere, and potential subsurface ocean continue to intrigue researchers. Each new piece of data contributes to a more nuanced understanding of the processes that govern planetary formation and evolution. Additionally, Pluto serves as a laboratory for studying the effects of extreme environments on celestial bodies. Understanding how Pluto and similar objects respond to solar radiation, cosmic rays, and temperature fluctuations can provide valuable insights into the behavior of other distant worlds. These findings are essential for understanding not only the history of our solar system but also the potential for life in the universe. As the exploration of Pluto continues to unfold, the potential for new discoveries remains high. The study of KBOs, their compositions, and their interactions with the solar wind opens up new avenues for research. Each mission and study adds a new layer to our understanding of these icy worlds, and the possibility of uncovering more about Pluto's history and geology is an exciting prospect for scientists and space enthusiasts alike. In conclusion, the journey of understanding Pluto is a testament to humanity's insatiable curiosity and drive for exploration. From its reclassification as a dwarf planet to the insights gained from the New Horizons mission, Pluto's story is rich with scientific and cultural significance. As we look toward the future, the exploration of Pluto and the Kuiper Belt promises to yield further revelations about our solar system and the nature of planetary bodies. Pluto stands as a symbol of exploration and discovery, challenging our assumptions and inspiring us to seek out the unknown. As we continue to study this distant world and its icy companions, we remind ourselves of the wonders that await us in the cosmos. The journey is ongoing, and each new discovery fuels our desire to understand the universe and our place within it. Ultimately, Pluto represents not only a celestial body but a reflection of our shared human experience, an embodiment of our quest for knowledge and our unyielding spirit of exploration. As we gaze up at the night sky and ponder the mysteries of the universe, we are reminded that there is always more to learn, more to explore, and more to discover. The legacy of Pluto, therefore, is one of inspiration and aspiration. It encourages us to continue seeking answers to the profound questions that define our existence, and to look beyond the horizons of our understanding. As we embark on this journey of discovery, Pluto will forever remain a beacon guiding us through the vastness of space and time, reminding us of the beauty and complexity of the universe we inhabit. Continuing our exploration of Pluto, we find ourselves drawn deeper into the complexities that characterize this dwarf planet and its environment. One of the most captivating aspects of Pluto is its geological diversity. The surface of Pluto is a tapestry of contrasting features, ranging from vast plains to towering mountains and deep valleys. The prominent region known as Sputnik Planitia, part of the larger Tambor Regio, showcases a heart-shaped expanse composed primarily of nitrogen ice. This unique formation has led scientists to hypothesize about the dynamic processes at play beneath the surface. One fascinating question that arises is how Pluto, situated so far from the Sun, can maintain geological activity. While it was once thought to be a static, cold world, evidence suggests that Pluto may have a subsurface ocean, a body of liquid water beneath its icy crust. This possibility opens up tantalizing questions about the history of thermal activity on Pluto and the role that radioactive decay may play in maintaining heat. It also invites comparisons to other celestial bodies, such as Europa and Enceladus, where subsurface oceans are believed to exist and where the potential for life is considered more plausible. The potential for a subsurface ocean is not merely speculative. Scientists have employed various methods to gather evidence supporting this theory. Measurements taken by New Horizons indicated that Pluto's surface features, including its large mountain ranges, exhibit signs of geological processes consistent with tectonic activity. The presence of chaotic terrain, regions where the surface has been disrupted and rearranged, further supports the idea that internal forces are shaping Pluto's landscape. The discovery of large ice mountains that reach elevations of over 3,500 meters suggests that Pluto is not merely a frozen relic but a world with an active geological history. As researchers continue to analyze the data from the New Horizons flyby, they are also investigating the possibility of cryovolcanism, volcanic activity driven by the eruption of volatile substances instead of molten rock. This process could explain some of the observed surface features and offers a compelling narrative for Pluto's geological evolution. By examining the shapes and distribution of various surface formations, scientists can piece together the timeline of Pluto's history and how it has changed over millions of years. Beyond its geological wonders, Pluto also boasts a complex atmosphere that adds another layer of intrigue to this distant world. Observations from New Horizons revealed that Pluto's atmosphere is predominantly composed of nitrogen, with traces of methane and carbon monoxide. The atmospheric pressure is much lower than Earth's, but it is still significant enough to support fascinating phenomena, such as hazes and clouds. One particularly captivating aspect of Pluto's atmosphere is its seasonal changes. As Pluto orbits the Sun, which takes about 248 Earth years, its distance from the Sun affects its atmospheric dynamics. During its approach to perihelion, the closest point to the Sun in its orbit, the increased solar radiation warms the surface, causing nitrogen ice to sublimate into gas, thickening the atmosphere. Conversely, as Pluto moves away from the Sun, the cooling process leads to the condensation of gas back into ice, resulting in a thinner atmosphere. These seasonal cycles create a unique environment that shapes the atmospheric conditions and influences the surface processes. The presence of atmospheric hazes, particularly those rich in hydrocarbons, reflects the intricate interplay between the surface and the atmosphere. These hazes can give rise to various optical phenomena, contributing to Pluto's enigmatic appearance. The study of Pluto's atmosphere also has broader implications for our understanding of other celestial bodies. By examining the processes that govern atmospheric behavior on Pluto, scientists can gain insights into the atmospheres of other KBOs and even exoplanets. The comparative analysis of atmospheres across different worlds enriches our understanding of planetary science and enhances our ability to detect and characterize potentially habitable environments beyond our solar system. Furthermore, the discoveries made at Pluto have prompted scientists to re-examine the criteria for classifying celestial bodies. The definition of a planet has long been a topic of debate, and Pluto's reclassification as a dwarf planet in 2006 highlighted the complexities involved in categorizing objects in our solar system. The ongoing dialogue about planetary status reflects a deeper philosophical inquiry into the nature of classification itself. Are we imposing our own definitions onto the cosmos, or are we merely reflecting the inherent diversity of celestial objects? As researchers continue to study Pluto, they are faced with new questions that challenge existing paradigms. For instance, what distinguishes a planet from a dwarf planet? Is the criterion of orbital dominance sufficient, or should other factors, such as geological activity and atmospheric characteristics, be considered? The case of Pluto serves as a reminder that our understanding of the cosmos is still evolving, and that each discovery prompts us to reevaluate our frameworks for understanding. The interest in Pluto has also led to a resurgence of public fascination with space science. The excitement generated by the New Horizons mission, combined with the ongoing exploration of the Kuiper Belt, has captured the imaginations of people around the world. As scientists continue to unveil new findings about Pluto, the public's engagement with space exploration fosters a sense of wonder and curiosity that transcends disciplinary boundaries. In the context of public engagement, educational initiatives play a crucial role in nurturing interest in planetary science. Outreach programs that connect students with scientists, provide hands-on learning experiences, and promote discussions about current research can inspire the next generation of explorers. By making science accessible and engaging, we can cultivate a more informed public that appreciates the intricacies of our universe. Moreover, Pluto's story serves as a valuable case study in the ethics of scientific inquiry. The debate surrounding its planetary status raises questions about how we approach classification, representation, and the language we use to discuss celestial bodies. As we strive to communicate scientific knowledge, it is essential to consider the implications of our terminology and the potential impact on public perception. In this context, Pluto can be viewed as a microcosm of broader societal debates regarding identity, belonging, and the definitions we construct in various aspects of life. The emotional resonance of Pluto's journey from planet to dwarf planet highlights the human desire to understand and categorize the world around us. Each reclassification, whether it pertains to celestial bodies or other aspects of life, invites reflection on the complexities of existence and the ways we navigate change. As we continue to explore Pluto and the Kuiper Belt, the prospect of future missions remains an exciting frontier. The advancements in technology and our growing understanding of planetary science open up new possibilities for exploration. Potential missions to other KBOs, such as 2014 MU-69 Arakath, which was visited by New Horizons, promise to deepen our understanding of the origins of our solar system and the formation of planetary bodies. Each mission into the outer reaches of the solar system brings with it the potential for groundbreaking discoveries that can reshape our understanding of planetary processes. The exploration of KBOs can yield insights into the conditions that existed in the early solar system, providing a glimpse into the building blocks of planets. As we gather more data, we can begin to piece together the puzzle of how our solar system evolved over billions of years. In summary, Pluto's journey is a testament to the enduring curiosity and ambition of humanity. From its complex geology and atmosphere to its cultural significance and philosophical implications, Pluto serves as a rich tapestry for exploration. The discoveries made through missions like New Horizons continue to inspire scientific inquiry and engage the public's imagination. As we move forward into the next era of space exploration, the story of Pluto will undoubtedly remain a cornerstone of our understanding of the solar system. The lessons learned from studying this distant world will guide future missions, fostering a sense of wonder and excitement about the mysteries that lie beyond our reach. With each new revelation, we come closer to unraveling the complexities of the universe, solidifying Pluto's place as both a scientific marvel and a symbol of exploration. In conclusion, the legacy of Pluto extends beyond its classification. It embodies the human spirit of exploration and the quest for knowledge. As we continue to explore the cosmos, let us remember that each discovery is not just a stepping stone toward understanding but a celebration of our shared curiosity. The story of Pluto is far from over, and as we gaze into the night sky, we are reminded that there are still many mysteries waiting to be unveiled. This video is for educational or entertainment purposes only, and information provided in the video may be incorrect. Like the video and subscribe to the channel for more such amazing videos.